Frequency modulation with synthesizers is a unique application of function composition. In its simplest form, we start with two sine waves. We'll call the first sine wave the carrier, and the second sine wave we'll call the modulator. This second sine wave will be modulating, which means changing, the frequency or pitch of the first sine wave. Using function notation, we can write those waves as the following. Carrier, we will say is y1 equal to a sine of 2 pi f1t. And for the modulator, we will write y2 equal b sine of 2 pi f2t. These are both functions of t standing for time, where f1 and f2 are the frequencies for the respective waves, a and b are the respective amplitudes, which means the highest output that can be reached, and the y's are the outputs at any point in time. The output for our purposes is voltage, which will also affect the volume of what we hear. When we use the modulator to change the frequency of the carrier, the resulting wave will have the following equation. Y equal to a sine of 2 pi f1t plus b sine of 2 pi f2t. It's important to notice that the modulator wave's output adds to the argument of the carrier wave, which means the frequency and the amplitude of the modulator play a role in modulating the frequency of the carrier. In fact, as b gets larger, the harmonic content grows. B is called the modulation index, which is equal to the ratio of the peak deviation, d, to the modulating frequency. We can write B as d divided by f2. Peak deviation is the maximum amount that the modulator frequency may deviate or be different from the carrier frequency. Furthermore, the amount of deviation is proportional to the amplitude of the modulator signal. The higher the amplitude, the greater the deviation, and the more modulation we will notice. So this modulation index, B, depends on the amplitude and the frequency of the modulator wave. To really understand this, let's listen to what this means. For this example, I'll set the carrier and modulator sine waves to 440 Hz. So F1 is equal to F2 is equal to 440. This is also an A on a piano. First, I will start with the volume down on the modulator wave. So in this case, D is equal to 0 and B is equal to 0. So no frequency modulation will be occurring. Now let's listen to what happens as I raise the amplitude or volume of the modulator, which means D and B are increasing. And let's also notice how the wave shape changes on the oscilloscope. With the modulator wave's amplitude at its highest volume, now I'll change the frequency of the modulator. This means I'm keeping D constant, but changing F2, which also means that B is changing. Think about how this sound is different from what we just heard when just the volume was changed. And finally, what if we change the frequency and amplitude of the modulator over time? I can simulate this by just turning knobs on the synthesizer that relate to the frequency and amplitude. Frequency modulation is a concept that actually predates synthesizers, as it is used in radio transmission, what we know as FM radio. It was invented in the early 20th century and was an improvement upon other transmission types, like AM radio, which uses amplitude modulation, which we discuss in another video. We can compare the visual difference by looking at the waveform of the modulator sine wave and comparing it to the resulting waves from amplitude and frequency modulation. In this first example, the top wave is the modulator, and the bottom is the frequency modulated wave. And in this second example, the top wave is the same modulator, and the bottom is the amplitude modulated wave. In the 1960s, using FM for sound creation on synthesizers was discovered by John Chowning at Stanford University. What he discovered was a powerful new way to create unheard sounds and emulations of known sounds. It was so powerful, Stanford University licensed the algorithm to Yamaha, earning the university $20 million before the license expired. We can use our equation from before to see some of what he discovered, starting with y equal a sine of 2 pi f1t plus b sine of 2 pi f2t. We can use the sum identity for sine and expand. From here, we have to rely on some higher mathematics like Fourier series and Bessel functions to write the resulting wave as y equal a times the summation from n equal negative infinity to infinity of j sub n of b sine of 2 pi f1t plus n 2 pi f2t. This represents a summation of an infinite amount of sine waves whose frequencies are represented as sums and differences of the two original frequencies, and whose amplitudes are determined by the terms j sub n of b, which take in the modulation index b and return a value for each integer n via the Bessel functions. To understand this simply, I'm going to set the carrier frequency to f1 equal 440 Hz, the modulator frequency to f2 equal 660 Hz, the modulation index to b equal to 0.1, and the amplitude of the carrier wave to a equal 1. From the equation, this means the resulting modulated wave will have equation y equal to the summation from n equal negative infinity to infinity of j sub n of 0.1 times sine of 440 times 2 pi t plus n 660 times 2 pi t. We can calculate a few terms by looking at n equal negative 2, negative 1, 0, 1, and 2. First, I can just plug in the numbers, and then I'll need to use some identities for sine and for the Bessel functions. And what we get for those values of n is that our modulated wave has these components: negative 0.00125 sine of 880 times 2 pi t plus 0.04994 sine of 220 times 2 pi t plus 0.9975 sine of 440 times 2 pi t plus 0.04994 sine of 1100 2 pi t plus 0.00125 sine of 1760 2 pi t. All of the amplitudes came from the table of Bessel function values. And again, keep in mind, this is only just 5 terms out of an infinite number that actually exist. So what we can see is that we have a sum of 5 sine waves with different frequencies and different amplitudes. Keep in mind that with lower amplitude values, 4 of these will not be as present as the carrier frequency, which has the highest amplitude. Also, for the one with negative amplitude, that simply means the sine wave is reflected vertically over the horizontal axis. But its sound is still present even if it is a low amplitude. For higher values of n in the positive or negative direction, the amplitudes become much smaller. Furthermore, for values of the modulation index b greater than 1, the frequency of the carrier will become less prominent than other frequencies. We can hear this modulated wave and see the component frequencies on the spectrum analyzer using the Yamaha DX7, which was one of the most popular commercial synthesizers sold by Yamaha using FM technology. So first, here's the sine wave with no modulation index. Keep in mind where you saw the peak, that was again the frequency of 440 Hz. And now I will bring in the modulation index up to that level of 0.10. We can hear a little bit more harmonic content to the sound wave, and we see little bars poking up that represent those frequencies that we were just discussing, but their amplitudes are very small. So now I'm going to raise the modulation index up to 5, and let's notice how those smaller amplitudes rise. The DX7 has 6 sine waves, each with control over their frequency, amplitude, and envelope amount, and it also has 32 algorithms for modulating routing. Brian Eno is one of the pioneers of FM synthesis. Many of his recordings since the 1980s have featured the Yamaha DX7 and other FM synths. Here is one example.